Hi everyone, and welcome to Lowell Observatory's live stream on the Leonids Meteor Shower peaking tonight. My name is Megan Gialluca. I'm a research assistant here at the observatory to astronomer Dr. Nick Moskovitz, who is also joining me tonight. He is an astronomer again at Lowell Observatory, and he's also the leader and founder of the Lowell Cameras for All-Sky Meteor Surveillance project. We're also joined tonight by Dr. Denis Vida, who is a postdoc at the University of Western Ontario, and he's one of the founders of the Global Meteor Network, which he'll tell us about tonight. So with that, I'll hand it off to, I believe Denis is presenting first.
Yeah, that's right. Can I start?
Yeah, absolutely. Before you do, I just want to remind everybody that up on your screen is the Lowell Discovery Telescope's all-sky camera. So we're going to be looking for meteors throughout the night. I'll stop anybody who's talking if I happen to see one. And then additionally, feel free to post questions in the chat box, and we'll get around to answering them as soon as possible. So you can go ahead, Denis.
Awesome, thanks. So I'm a postdoctoral associate at the University of Western Ontario. That's basically when you finish your PhD, they give you this position, and they basically tell you, well, figure out what you're going to do for your research, and maybe we're going to keep you around longer and give you a professorship position, and it can last for, let's say, 5 or so years, maybe sometimes even longer. My main focus of research is meteor astronomy, and actually as a side project, I started the Global Meteor Network, which is a project that deploys meteor cameras worldwide and ensures that no big major meteor events go unnoticed and unrecorded. Before I get into that, I first want to talk about some basic terminology. So meteor astronomers are not very imaginative people, and they tend to call everything a very similar name. So first we have to define what a meteoroid is. So that's basically the rock that's out in space. Once that rock collides with the Earth's atmosphere and starts burning, we call that a meteor if it's smaller, and we call it a fireball if it's very bright. Now, if this object was very big, bigger than, let's say, 1 meter, and is a very small velocity, so it's basically very slow, it can produce a meteorite on the ground. We also have other types of meteoroids that are smaller, dust particles, and they're cometary, and they usually cause meteor showers like the Leonids we're going to be talking about today. So the way meteoroids originate is from comets. So these are big icy bodies which usually reside in the outer solar system, but their orbits take them closer to the sun, and they start heating up. And the trapped ices beneath the surface, and that could be water ice, it can be CO2 ice, it can be carbon monoxide ice. They start sublimating, and they take dust particles off the surface into an orbit that's close to the orbit of the comet. And then what happens is that planets in the solar system tug onto these dust particles and make them change their orbit. And also the solar radiation pressure, basically like the sunlight, pushes these particles away or closer towards the sun and forms these very complex meteoroid streams in the solar system. Now, what's interesting is that the older streams can be quite complex and dispersed, but the younger streams, they're very compact. So when a younger stream intersects the Earth's atmosphere, we see a big meteor shower outburst. We see a lot of meteors at the same time. So basically what an observer on the ground would see is a lot of meteors on very similar trajectories coming in, and due to a simple perspective effect, it appears as if they're coming from the same point on the sky, which we call the radiant. So what's actually going on physically is that these millimeter-sized particles collide with air molecules in the atmosphere, very high up at about 100 kilometers or 60 miles. So people are usually surprised, oh, I thought these were bigger, but in fact, most meteors that you can see on the night sky are about a couple of millimeters in size. So that's the, let's say, 1/10 of an inch, I guess. So what happens is that their surface starts heating up, and because they're usually rocky, the surface literally starts to vaporize, and we call that process ablation. And that keeps going on until there's basically nothing left. And only very recently we started to understand that meteor fragmentation is a very important thing. So they basically crumble into smaller pieces, and particularly one mode of fragmentation, which is called erosion, seems to be particularly important. And that's basically these tiny little micrometer-sized grains get detached from the surface and they start ablating independently. And once ablation is done, at the end, there's basically nothing left. The whole rock just ends up as a bunch of dissociated ions and electrons up high in the atmosphere. Now, that's the small stuff. How about the bigger stuff? Well, the big stuff can usually produce meteorites. And meteorites are basically crushed up asteroids. So you have these big asteroids in the solar system. They collide with one another, and they produce these meteor-sized objects that when they enter the Earth's atmosphere can produce meteorites. Now, meteorites are extremely important because they are the best evidence we have for the formation and the evolution of the solar system. So that's basically a rock that was untouched almost for billions of years. So if you can analyze that rock, you can see how the solar system was in its youth, right? The problem is that out of about 40,000 known meteorites, only 50 have known orbits. So most of the meteorites were found by people just, walking along and, well, I see a weird rock and turns out, well, it's not from Earth. It has a very different chemical composition and it's a meteorite. But only in the last 70 years or so, people started deploying all sky meteor cameras and started observing meteorite falls. And then what you can do is you can connect this rock to a particular orbit in the solar system. And you can say, oh, you know what? This rock came from that particular asteroid. So instead of spending millions of dollars to send the OSIRIS-REx or Hayabusa to a particular asteroid to do samples, what you can actually do is just deploy meteor cameras and wait until those rocks come to you. And it's even better because you can put that rock in a lab and you got kilograms of material instead of these tiny dust samples, right? And today, we actually, the meteorite science advanced so much that we can actually pinpoint individual rocks and meteorites to particular craters on certain asteroids. And the small stuff is very important when it comes to safety in low Earth orbit. So the last couple of years, people started launching a lot of stuff in low Earth orbit, and there's obviously going to be increased human presence in space and low Earth orbit with all the private companies are going to do all the, going to launch a lot of new rockets and projects and whatnot. And the problem is that even though this tiny piece of dust is so small, it's traveling at 20 kilometers a second, and it has the same kinetic energy as a rifle bullet. So when an astronaut is doing a spacewalk, NASA basically tells them, well, there's 1 in 5,000 chance you're basically going to die due to a meteoroid hit. So, and that is for nominal meteoroid activity. So that's basically a couple of meteors an hour that you can see on the sky. But when that rate goes up, when you have a huge meteor shower outburst, well, instead of 1 to 5,000, it basically climbs to almost to 100%, right? So we want to predict very accurately future meteor shower outbursts to make sure that people in orbit and all satellites and other space resources are safe. And in fact, there were some accidents in the past. So in '93, there was a big Perseid meteor shower outburst, and a European Space Agency satellite, Olympus-1, which is the biggest commercial satellite at the time, got hit by a Perseid meteor, and the plasma cloud that it produced shorted some electronics inside. The satellite lost attitude control, it started spinning, And in the end, they were able to stabilize it, but it spent all the fuel and it was basically rendered useless. Also, one scientific instrument called XMM-Newton, which is this X-ray observatory, it was looking in one source of meteoroids, and in two different events in 2005 and 2012, it was hit by two different small meteoroids in its cameras and basically lost more than 50% of its scientific capacity. So basically, meteor shower outbursts are then extremely important to predict and understand when they're going to happen, because we want to keep people and stuff that's in orbit safe. But in fact, they're notoriously hard to predict. Let me illustrate that. So in 2011, a lot of scientists predicted there's going to be a big draconic outburst, and people took their meteor cameras, put them outside, they made a lot of observations, they published a lot of papers, and we know a lot about that meteor shower now. And the nominal activity was about 300 meters per hour. Just for reference, NASA will cancel spacewalks when the rate goes up to about 150 meters per hour. That's for the Perseids and the Geminids. But in 2012, they didn't predict an outburst. And it turns out the peak of that outburst that actually occurred happened over Central Asia. We didn't really have any meteor cameras there to understand what's going on. And it turns out it was this huge meteor storm of 9,000 meteors an hour. And it was caught only by chance by a bored grad student who was looking at our meteor radar data during Christmas holidays. So it basically tells us we need more meteor cameras to get a better understanding in real time of near-Earth meteor environment. So that's why we started a Global Meteor Network project, which currently consists of about 250 stations in 20 plus countries all over the world. Currently, the network is mostly concentrated in Europe and North America. And the way we designed this network is that we didn't want to be directly responsible for funding, maintenance, and basically everything of the project, because it would take a lot of time from our scientific work. And we want to provide amateur astronomers with the possibility to participate in the project and contribute good scientific data and be good citizen scientists. So what we have is a very low cost system, costs about $400, and it's basically a fully automated meteor system. Does meteor detection, calibration, data reduction, and this is how the data looks like. So the meteor cameras that we use are very sensitive. They were actually developed for dash cams. Apparently, it's very important to have good visibility during the night. And we use Raspberry Pi single board computers as the main heart of the system that does all the processing. So on our limiting magnitude is around magnitude 6 at 25 frames per second. So it's not really a long exposure. And we see a lot of meteor showers. During the Geminids, for example, one camera can see more than 1,000 meteors a night. And we also see a lot of meteorite dropping fireballs, which is exactly what we want to get a better understanding of origins of meteorites. And compared to some other all-sky cameras, we can also see details of fragmentation and other things that can help us to constrain physical properties of these bodies, which is exactly what we want. One other aspect is that we also see a lot of TLEs, basically atmosphere lightning, sprites and elves, et cetera, which we don't really use, but we have a big archive of that data. So if there is anyone interested in atmosphere science or doing anything with that and is interested in this data, we can actually provide provide a large archive of that. So as I said before, this is how the system looks like. We currently use Raspberry Pi 4s, and with these sensors, we get fields of view of about 90 times 45 degrees. And if you want to build this system in parts, it's about $250. But we also have a private company partner that can sell you, and you can buy a plug-and-play system for about $450. And I think I ran out of my time, so thank you for your attention. And do you have any questions?
Thank you so much, Dennis. We actually did get a question while you were talking. So this is from Lunar Eclipse. At Lowell Observatory, what determines the brightness of a meteor or meteoroid, or was that already said?
Yeah, as for the brightness, it's mostly the mass and the speed. So the faster it is, the brighter it is, and the larger it is, the brighter it is. And there's also some modes of fragmentation involved. So for example, if you have a meteor that's kind of a rock that's not fragmenting, it will slowly go up and it will have a peak, and then it will slowly go down. Now, if at one point meteor fragments into many pieces, the light curve, the brightness will shoot up very quickly, and then it will just die out.
Fantastic, thank you. I also noticed one other question a little bit earlier in the stream, which was from Chris L., which is, how did the meteorite over Russia go undetected? I'm assuming he's talking about Chelyabinsk here.
Yeah, that's a good question. I actually might have a slide that shows that. So if you can give me a few seconds. No, it's not in this one. So it was about a 20-meter size asteroid, and it turns out that it came from the sunlit side of the Earth. So that basically means no telescopes could actually detect it because it was daytime, right? We couldn't see it coming. And we actually ran the analysis to check if it was detectable at any point in the last 10 years by any asteroid surveys. Here's a slide. And turns out, well, no, it was actually too faint to be detected. And the next thing you can ask is, well, how many of them are still undetected? Well, it turns out we know less than 1% of these 20-meter size objects, but they don't really pose a big threat. What we're currently concentrating on are 140-meter size asteroids, which are kind of that hit, so it would be an unprecedented disaster in human history. And hopefully by the end of the decade, we'll know about 70 up to 80% of them.
Awesome, thank you. It's really interesting. One more question for you from Danny Balanon. Hopefully I said that right. What is the record for the largest meteorite?
Oh, that's a good question. It's really hard to say, and I can't really tell you on top of my head. It's the largest, say, craters that we have. In a sense, the question loses meaning, because if you have a really huge impact, it gets embedded in Earth's crust, and it's not like an individual rock. So in a sense, probably the largest meteorite or whatever you can think about was that, planetesimal that hit us when Earth was young. It was the size of Mars, and its material got embedded within Earth and created the moon. So you can almost say that the moon is the largest meteorite in that regard.
I think that's a cheating answer, personally.
Well, I can add to that answer with maybe the other side of that. I mean, I agree with Dennis that if you have a really big impactor, it's just going to vaporize and sort of sink down. And, all of these big mass extinction events like the Chicxulub impactor that we think contributed to wiping out the dinosaurs, there's no pieces of that left because it's such a massive impact. It's just gets mixed in the sort of magma crater that's created with the huge energy of impact. But with that said, there are some very large meteorites that we have in our collections. And I think the largest is a large iron in Namibia that is maybe car size kind of thing. It's maybe a few meters across. And I remember seeing photos of it. It's some sort of square block thing. And I forget the actual name of it. We could probably Google it pretty quickly.
Actually, somebody in the chat said that it's named Hoba.
Yes.
Does that ring a bell? Mm-hmm.
Yep, that's it. And I don't know the exact size, but it's big. I mean, it's got they excavated around it, and there's an amphitheater around it where you can go check it out. I've never seen it myself, but I think that's the largest on Earth, the largest single rock that's still intact from space.
Awesome. One more question. from Dr. K. Carr. If I use a 600 millimeter lens on a DSLR camera, can I see or capture a meteor as clearly as with a high-power telescope?
The thing with meteors is that you don't really need a high-powered telescope. In fact, what you need is a very sensitive wide field camera. So you need a large field of view because meteors usually traverse tens of degrees on the sky, right? So if you have a telescope, you'll have a very narrow field of view, so you only just see portions of meteors. And you basically just want to get whole meteor tracks to be able to reconstruct the trajectory. So in fact, you can basically use normal, let's say 50 millimeter lenses on DSLRs, as long as you can run them at a high frame rate, let's say 25 frames per second. In fact, we did try using like Sony cameras and just using them for meteor detection, and it actually works just fine.
Cool. Another question from Georgia. What time of the year has the best meteor showers?
Ooh, that's a good question. If you don't mind the cold, I would say December and January. The Geminids are very impressive. The only issue is that it can get quite cold in mid-December, and in some parts of the world, it's also, the weather is pretty bad. And also the quadrantids are amazing, which happen like the 3rd, 4th, 5th January. But if you are just a casual observer, then I would say the Perseids in mid-August. It's always nice and warm outside, and the weather is usually nice, and you can expect to see some nice meteors.
I would agree with that.
I mean, you kind of, just to follow on to that, I think you alluded to this, Dennis, that meteor showers can be unpredictable. And that's kind of the exciting thing about them, is you never really know. We make the best guesses we can about what the rates of meteors are going to be. But it's a complex problem, as you showed in some of those animations, and anything can happen, essentially. And the one that we're kind of going to be talking about tonight, the Leonids, maybe have a better track record of having clear predictions, but every few decades they experience meteor storms, so huge outbursts of meteors. And so, in the case of the Leonids, we can actually predict ahead of time when those storms are going to happen, and so that that's a once in a lifetime kind of event if you can see one of those.
Pretty much.
But yeah, that's part of the excitement, because you never really know what you're going to get.
Yeah, the Leonids are really cool because they're one of those meteor showers that's talked a lot about in like historical texts, especially in in Asia, really. But anyways, I'll get back to the questions here. So I think one more question, and then Nick, I'll turn it over to you so you can talk about Lowell's efforts and how to view the shower tonight. So this question also from Dr. K. Carr. Thanks, Dr. Vida and Megan. You're welcome. What if I want to see some in larger form? Does longer focal length help or hurt? So I think what he means here is, what if he wants to see like a zoomed in meteor?
Oh, yeah, that's a good question. So to see a zoomed in meteor, you need to have a meteor tracking system. And that's actually something we have here at Western. We have an 80 millimeter apochromatic telescope, at the end of which there are 2 mirrors. And we have a separate camera, a wide field camera. When it detects a meteor, it cues the mirrors and tracks the meteor through the telescope, at the end of which we have another camera. So you can see meteors really close up, see how they fragment, and like the details of the morphology. I can pull up some videos later if you like. It's really cool, but it's I'd say one of a kind system.
Yeah, that's super cool. I definitely think we'd like to see that later tonight. Yep. So before I turn it over to Nick, I just want to remind everyone that what you're seeing on your screen is the Lowell Discovery Telescope's all-sky camera. In the right of the all-sky camera, you can actually see the Lowell Discovery Telescope. And fun fact, you see a little green crosshair in the all-sky camera footage. That's actually where the telescope is pointed right now. So they are doing research on the telescope tonight, and you can see where it's looking. So with that, we're going to take a break from the questions, but keep them coming. I still see all the questions, and I'll get back to them as soon as Nick is done talking. But I'll turn it over to you so you can tell us a little bit more about stuff.
Okay, great. Thanks, Megan. Okay, so I'm going to kind of pick up where Denis left off and talk a little bit about some of the efforts we have ongoing here at Lowell involving the observations, video observations of meteors. And this is work that I'm carrying out along with Megan, who's been helping me out as a research assistant on this project. And Denis has been a great deal of help, as you'll see when I move through these slides. We're leveraging his Global Meteor Network infrastructure, both in terms of hardware design and in terms of the software that we're using to drive those cameras. So I'm going to talk about the efforts we have going on here at Lowell, and then sort of the last few slides, I'll talk about the Leonids specifically, viewing tips, where you should go to watch them, when you can see them, things like that. So I've been working for just a few years in the sort of world of meteor science, and this has been kind of a side project for several years now, where we've set up camera systems at a few sites around northern Arizona to take video recordings of meteors. And we currently have 4 camera stations that are set up. These actually leverage the heritage from another type of meteor camera system known as CAMS, Cameras for All-Sky Meteor Surveillance. CAMS was started by a guy named Peter Yenniskens at the SETI Institute in California. And so we learned a lot from Peter about how to build these systems and deploy them and collect the data and process the data. And you can see here the 4 stations that we have deployed. We have one up in Mars Hill, just outside of Flagstaff on the main Lowell Observatory campus. We have a box here that's just outside the Lowell Discovery Telescope. So this is the same telescope that you see in the corner of that all-sky camera image. We worked with collaborators at Embry-Riddle Aeronautical University in Prescott, southwest of Flagstaff. And then most recently, we deployed a station out at Meteor Crater, which just seems like an obvious thing to have meteor cameras out at Meteor Crater. So we did that, and we installed it on the roof of their visitor center, which was a great place to hang out at night. It's an amazing view looking out over the crater, and it's an incredibly dark site and wonderfully clear skies for doing nighttime viewing. So we've got those 4 stations running. And the reason we have multiple stations is so that we can triangulate the position of meteors. And this is a sort of Google Earth image. Here are schematically shown the 4 locations of our stations out in Prescott at Embry-Riddle, at Lowell's Discovery Telescope, Mars Hill, and Flagstaff and Meteor Crater. So we've got our 4 stations. And when a meteor comes in, we actually are viewing that meteor from multiple vantage points because we have these cameras separated by many tens of miles. And so they're seeing these meteors from different vantage points. And that allows us to triangulate their positions. And so what this Google Earth image is showing is actually a real meteor that was detected by these stations. And you can see the trajectory here with the sort of red arrow pointing down. And this is sort of a typical event that we would see. In the sense that it's typical altitude, typical speed. This is the kind of information that we're able to obtain when we combine the data collected from these multiple camera systems. And I show a video example of a fairly bright meteor that was picked up by our cameras. But the important thing here is actually, the meteor is cool to look at. There's interesting structure in the meteor, and it actually flares pretty bright, causing interesting reflections and things like that. But the way we do this is we're actually looking at the background stars that you can see as the faint dots in this video here. And we use those stars to triangulate the position of the meteor, because the stars that, for example, the Mars Hill camera sees are going to be different than the background stars that Meteor Crater sees. And that's because they're looking at that event from different angles. And so the background stars are going to be different, and that allows us to reconstruct that trajectory. This is a phenomenon widely used in astronomy known as parallax. It's used throughout many different areas of astronomy, not just meteor science, but it's a convenient physical phenomenon that we take advantage of to reconstruct these trajectories. So that's the sort of existing state of our networks. I want to talk a little bit about moving forward and the work that we're going to be doing in the coming months and years as we're ramping up activity on a new project here at Lowell. And we're working with Denis on this, taking advantage of, again, the hardware infrastructure that he developed as part of the Global Meteor Network. And as Denis said, these cameras are fairly simple board cameras. You can see our prototype array here set up, where we have 6 of these board cameras set up. Each one of those is powered by its own Raspberry Pi board computer. So these are little board computers, very popular in the sort of hobbyist market, really low cost, but incredibly powerful for being so low cost. So each of these computers, you can see the stack of all 6 of them here, powers one of these cameras. And those all live within an enclosure. And the enclosure here is open, but we would put the lid on and there's a dome on top. And we can see this is our sort of first prototype that just started running a few weeks ago, thanks in part to significant effort by Megan in getting this system assembled and built. And it's been collecting data now. We're still refining the process and how we want these to run and things like that. But here's a nice example from sort of last month's major meteor shower, the Orionids, where you can see a mosaic here that Denis actually put together, or sort of photoshopped things together here to show all the meteors that were detected by these cameras in a single night. And again, this was on a night of the Orionids, and so we're looking at sort of an unusual level of activity here, but it was of order, I think, 1,500 or so events in a single night. And so each one of these little streaks in this image is a meteor, with the exception of a few of them where these are actually planes and satellites that sneak their way into our video footage, because our cameras are very good at seeing moving things in the night sky. And so that can be meteors, but it can also be planes, it can be satellites, it can be bugs, it can be clouds, it can be anything that goes bump in the night, essentially. The streaks, the sort of faint gray streaks in the background are stars that are trailed. And you can see, for example, the North Star up here at the top of the image. And so these cameras, when we tile things together like this, are essentially creating all sky coverage from zenith, so directly overhead, down to about 30 degrees above the horizon. So we've got this prototype up and running. We're working on building our second prototype of this system. And with those 2 up and running, we'll then be able to do the triangulation exercise that we have been doing with our other meteor cameras that have been running for a couple of years now. And so what does the future of our network look like? Well, as I said, this is sort of a project that's starting to ramp up. The National Science Foundation has funded us for the next 5 years to do this, to conduct a significant expansion of this network of meteor cameras. Again, we're going to be leveraging the Global Meteor Network infrastructure, software and hardware design. And so here's our sort of current deployment of stations. As I mentioned earlier, we have Embry-Riddle and Mars Hill and Lowell Discovery Telescope and Meteor Crater. And this is sort of the coverage that we achieve in sort of northern Arizona. It's an approximate map of the sort of region above Arizona that we're covering with our cameras. And the effort that we're going to be seeing over the next couple of years is a significant expansion of those cameras. And so the next few locations that we're looking to expand to are shown here as the yellow stars. So we'll be sort of adding to this network and building outwards over time. I think over the next sort of 6 months or so, we'll see these stations go in. Again, these stations we expect to be very similar to our prototype that's up at Mars Hill. The 6 camera systems all being run by Raspberry Pis. And then further ahead over the next year or 2, we're looking at additional sites beyond that sort of core network. And then, there's a lot of open frontier out here. And of course, we're not the only people operating meteor cameras. There's a really great network of global meteor systems in New Mexico. And so if we expand far enough east, we'll be able to join up with that network. There's networks in California, both GMN and other flavors of meteor cameras. So the intent is to really achieve, large regional coverage and fill some of this frontier here that is currently uncovered. And we're looking forward to that expansion process over the next year or 2. one of the really exciting aspects of this project is not so much about the science, but really about sharing the science with the world, is an exhibit that is actively being developed now. And I just wanted to show this because it's been really fun actually thinking about how to share the data and the science of meteors with visitors who would be coming to Lowell, coming to Meteor Crater, and potentially finding us online. So this is an exhibit that's being developed in collaboration with Northern Arizona University and their Advanced Media Lab, again, funded by the National Science Foundation. And the intent for this exhibit is to build a large format touchscreen media wall in which people can interact with the stream of data that our cameras are collecting, so that when visitors come up to this exhibit, they'll be seeing data that were captured just the night before. So it's a way to connect people to sort of the ongoing science and the ongoing data collection associated with these meteor camera systems. So the hardware for this exhibit has just arrived in the past couple of weeks, and the folks at NAU are working hard with the development of this exhibit. And so it's definitely something we're looking forward to, and hopefully we'll be deploying at Lowell, deploying at Lowell and at Meteor Crater. So we'll be doing 2 exhibits and aiming for sort of next year timeframe for the first of those to be deployed. So come see us at either Lowell or Meteor Crater, and hopefully you'll be able to check out that exhibit. So the last thing I want to mention, and this is kind of related to this NSF project, is going back to one of the first slides that Denis showed of this connection between meteoroid, meteors, and meteorites. And I think, Denis alluded to this in the sense that really one of the powerful things that we can do in meteor science is observe these objects coming in through the atmosphere, understand where they're coming from in the solar system, and then for the particularly big events, go and pick up freshly fallen rocks. So meteorites that have just landed are not heavily weathered or altered by Earth's atmosphere and represent this primordial state of the solar system. And so this characterization of that material from the meteoroid, the pre-impact state, through the meteor phase down to the meteorite can really take advantage of sort of next generation systems that are coming online. And GMN and the meteor networks are just one part of that. I think it really starts, and what many in the astronomy world are looking forward to is the deployment of large-scale all-sky telescopic surveys. And this is one example here, the Large Synoptic Survey Telescope, or the Vera Rubin Observatory, that's currently being built in Chile. This is a fairly recent picture of that building. You can see pickup trucks for scale down here in the lower part of this image. It's a truly impressive facility that's being brought online. And this is an 8-meter telescope. This is a large telescope that's going to be surveying the night sky every few days. And the entire sky will be seen to unprecedented depths every few days. And so when an object, when a facility like this comes online, we'll all of a sudden be discovering all kinds of things that we've never even realized were out there before. And one of the things that may be well suited to detecting are little streaks of asteroids or meteoroids coming through the field of view. And that might look something like this, where you have background field stars and sort of planetary streak or a meteoroid passing through that field of view. And in rare cases, those meteoroids, with a bit of luck and enough cameras on the ground, those meteoroids could be picked up by cameras like those that Denis talked about and that we're trying to deploy here at Lowell. So now you could have an event that not only you watch coming through the atmosphere as a meteor, but you may have LSST or other surveys collect data of that rock before it's even hit the atmosphere. So you're studying that object in space before it's going through this violent ablation and vaporization process. And then, of course, the really big events are going to produce rocks on the ground. So you get to that final meteorite stage where you go out and you look in a search region, a strew field, and hopefully collect those freshly fallen meteorites. And so this sort of end-to-end characterization from the telescopic through the video cameras to the meteorite collection, hopefully the analysis of those meteorites in the lab, that's something that I think we all are striving to improve our methods and our ability to achieve, because it's a rare occurrence when you can link these different parts of the chain. And certainly the efforts that Denis is talking about with the Global Meteor Network is a critical part of being able to bridge that gap between the telescopic data and the meteorite collection on the ground. So with that, I'm going to transition now over to the Leonids and talk about tonight. And I've just got 2 slides on this. So we'll start just by talking about what are the Leonids. So Leonids are produced by a parent comet, 55P Tempel-Tuttle. 55P is on a 33-year orbit around the sun. And we're seeing sort of a bird's eye view of the solar system here, where all the small circles in the middle of this diagram are the terrestrial planets, Mercury, Venus, Earth, Mars. And then we have Jupiter, Saturn, Uranus, and Neptune as the outer rings here. And so you can see the orbit of Comet 55P is on this eccentric cometary-like orbit that brings it in to the inner solar system and actually intersects very nearly the orbit of the Earth. So that's why we get meteor showers from 55P, because it deposits its material as it comes into the inner solar system. When the Earth intersects that stream of material, we see meteors. And here's an image of actually, or a simulation, I guess you could say, of meteors detected by the CAMS, meteor camera systems, of Leonid meteors. And you can see the triangulation that was used to generate the orbits for these meteors show that they fill an orbit that very closely resembles that of 55P. And that's really one of the strongest pieces of evidence we have for a meteor shower being associated with a specific parent body. When you see this close orbital alignment or orbital similarity between the comet in this case and these meteors. I mentioned earlier that 55P and the Leonids generate meteor storms, and I'll talk about that on the next slide. But these are periodic in the sense that every 33 years or so, 55P comes into the inner solar system, releases material, and when the Earth intersects that stream of material, we see an outburst of meteors. And these outbursts can be quite dramatic. Denis showed a famous carving, I think it was a wood carving of the outburst in 1833, where the number of meteors was truly staggering. And I'll hold off until the next slide to say what the number actually was. So the Leonids peak in mid-November. They're a fairly high impact speed. So when you're going out and looking tonight, that means they're going to be pretty quick flashes, and so you got to kind of keep your eyes peeled to catch them. They come in, the relative velocity with the Earth, or the impact speed with the Earth, is 71 kilometers per second, or 158,000 miles per hour, which is kind of a staggering number to think about. And they're relatively high meteor in the sense that their beginning height at which they start to ablate, or at least become luminous, is around 120 kilometers, 75 miles up in the atmosphere. And there have been examples of the Leonids even higher up in the atmosphere. So, as I mentioned, the Leonids produce these dramatic storms. And there are accounts throughout history about these events. And as I said earlier, these would be truly a once-in-a-lifetime experience to see something as dramatic as some of these Leonid outbursts, or really any major outburst of a meteor shower. And so I'm just showing one example of sort of an historical count that I think is particularly cool of the Leonid storm in 1833. And so this is a very famous painting on a hide here, as known as the Lone Dog Winter Count. And I'm absolutely not an expert in Aboriginal history or anything like that. I just find this really cool, and so I think it's kind of fun to show. But so this is a winter count, which is essentially an annual telling of major events for a given year, produced by, in this case, Lone Dog was the name of the man who produced this annual account. And this is 70 years, I believe, or 72 years of summary of his experience as a a Sioux Indian in the Central Americas. And so every one of these icons corresponds to the seminal event for that year that Lone Dog and others of his community decided was the most important event of that year. And I don't know what all of these represent. The chronology here, I believe, starts in the middle and spirals outwards, starting in around 1800. And when you get to 1833, there's this little icon here, which is showing a crescent moon and stars falling. And this is a recording of the 1833 Leonid outburst. The winter count of that year was determined that this outburst was the most significant thing to have happened. And one of the reasons for that is it was of order 100, estimated that 100,000 meteors per hour happened over a fairly short window that was only observable over North America, maybe 8 hours or so, in which this just meteor storm produced a huge number of meteors that would have just been amazing to witness. And at a time back then, I mean, not everyone really, not even the scientific community didn't really understand where these meteors were coming from. At that point, it was not linked. This shower is not linked to Tempel-Tuttle. And so it must have been just an incredible experience to sit there and just watch, the sky fall, essentially. And so this is, in the case of the Leonids, this repeats with that orbital period of the comet. And so, unfortunately, this year we don't think one is going to have one of these outbursts. But I'll tell you on the next slide here when the next one is, and that's not until 2031. So we'll come back to you in 2031 and share all the outbursting activity that's going on. But this year, in the 2020 Leonids, one of the best things for this year's shower is that it's almost new moon. So that means skies are dark. It's a great time to go out and watch meteors. We don't have a full moon that causes glare and makes it hard to see the meteors. This year, we expect something like 10 to 20 meteors per hour. Again, we don't think it's going to undergo a major outburst. The next major one for the Leonids is probably not until 2031. Denis mentioned this earlier, where the position in the sky, which is shown here in the crosses, that's what we refer to as the radiant, and that's where it appears that all the meteors are coming from. And so if I draw a line back from each of these meteors collected in this image, they all sort of point back to a radiant position. And that radiant position happens to live in the constellation Leo. And so that's where this shower gets its name, the Leonids. This is a stellarium image of tonight at 2 a.m. As viewed from Flagstaff. So off to the east around, sort of after midnight is when Leo starts rising. And that's where the radiant position is. But the thing that maybe is a little bit clearer from this image at the top is that while all of these meteors do point back to the radiant, they can appear almost anywhere in the sky. And so you don't have to have a view of the radiant to see the Leonids. It's enough to find a good viewing location, and I'll talk about that next year, about what a good viewing location is. But it's enough to find a good viewing location that has a clear view of the sky. And as long as you're seeing sort of overhead and preferably maybe off to the east, you do have a chance of picking up some of the Leonids. So viewing tips for tonight: go out, find a dark site, avoid ambient lights, street lights, outdoor lights of any kind. You don't want that to get in the way. Get comfortable. This is the kind of thing where you want to get comfortable, stay warm, find a comfortable seat, and be patient. It's not the kind of thing where the minute you step outside, you're going to start seeing meteors falling. You want to wait. 10 to 20 meteors an hour is a decent show, but it's not the biggest of the year. So be patient. Avoid screens. Don't be looking at your phone. Don't be looking at your laptop. You want your eyes to acclimate to the dark, and that can take 15, 20 minutes. And so give yourself some time to your eyes to adjust and become sensitive to these meteors that, as I said earlier, they're fast and in many cases faint. So you got to kind of be ready to catch them when they come. The best time to watch is between midnight and dawn. That's not to say that we may not see some tonight while we're watching the all-sky camera after this presentation. But the best time is going to be between midnight and dawn, and that's independent of where you are on Earth. Essentially, the peak of the shower is going to be about the same window for every location. So if you're here in Arizona, wait a couple hours. That's when the peak is going to be. If you're somewhere else, between midnight and dawn is your best chance. And then, I think the best instrument you have for watching meteors are your eyes. You don't need binoculars or a telescope. I think you would make it harder on yourself by trying to catch a meteor with some kind of instrument like that. You just can't swing the binoculars or telescope around fast enough to be able to catch these things that are moving so quickly. So just go out, get comfortable, lay back, and look up at the sky, and hopefully you catch a few good events tonight. So that, I think, that is the extent of what I have to present. So I haven't been keeping an eye on the questions, but I'm happy to take questions at this point, and we can transition over to the all-sky camera as well and start looking for meteors there that may show up.
Yeah, so while the all-sky camera is up, I just want to quickly point out that we can see 3 of the fairly bright planets tonight. So in the bottom right underneath the Lowell Discovery Telescope, we can see Jupiter and Saturn. Jupiter and Saturn will be the brighter ones there. And I believe one of our people working behind the scenes can point that out with their mouse. And then additionally, we can see Mars, which is in the center bottom. So that's also a fairly bright planet, one of the closest ones to us. So while you were talking, we did get a couple of questions. So the first one is from Chris L. How many meteors hit Earth in a year on average?
That's a good question. We can probably speak in terms of mass than in terms of numbers. I would say the answer is disappointing, because we try to measure the mass in many different ways. And I actually have slides for all the questions that were asked, believe it or not. I just have to pull them up quickly. So let me just share my screen again, if that's okay, unless we want to watch the all sky camera. Is that possible?
I think you can share your screen. I don't see why not.
Okay. Yep. As long as it works. Okay. Can you see this, guys?
Yep.
Okay. So basically, the question is, how many meteors arrive to Earth every day? And we can do different types of measurements. We can do what's called an extraterrestrial estimate. So basically, you have something in space that's counting how many meteoroids go through a certain area, right? We can also have a middle atmosphere estimate, which is basically have a bunch of meteor cameras, which count meteors and their masses and produces a count. Or you can have what's called a ground accretion estimate. So you basically go to Antarctica and you get ice cores and you get sediments from oceans, and you basically count how many extraterrestrial deposits. And by extraterrestrial, I basically mean material that is not from Earth, has nothing to do with aliens, right? And one way to do it, and that's what NASA did back in the 80s, is they put up a school bus-sized satellite, which is basically didn't really have any electronics, didn't have any motors on it or nothing. It was literally just this huge metal cylinder that spent about 6 years in orbit. And after that, they took it down and they counted how many little craters were on every different plate. So they put up like a gold plate, an aluminum plate, a Kevlar plate, and every type of material had different strength, and then it would produce different kinds of craters. And from that, they could derive how many objects of what mass arrive to Earth every day. And if we look at the numbers from different methods, you can see that the numbers vary widely because all of these methods have different biases and problems. But I think right now the most accepted figure is about 43 tons per day. Although it can vary from about 5 tons to about 200 tons, depending on how you measure it. So
that feels like a lot.
Yeah, pretty much.
Yeah, I mean, the number, that's roughly the number that I say when people ask that, is 50 tons a day. And the telescope over my shoulder here, the Lowell Discovery Telescope, that's about the weight or the mass of the Lowell Discovery Telescope is about 50 tons. So take that and vaporize it and distribute it across the globe every day. That's how much material we get. But it's also very stochastic, right? So in 2013, when we got hit by Chelyabinsk, the Chelyabinsk impactor, I don't actually know the mass of that, but I suspect that 2013 had a huge spike up because of that big impactor event. And these are, the once every few decade kind of events that are going to cause things to really kick up when you have those rare events happen.
Cool. So the next question comes from Leandro. So are meteor showers predicted by their streams? Are young streams or old ones more common to cause showers / meteors on Earth?
Yeah, that's a pretty good question. I'd say it really depends on the shower. We can't really draw general conclusions, but for, how can I say, annual meteor showers that produce constant rates. And
sorry, I'm going to interrupt you real quick because I'm getting word that there's a possible meteor above Betelgeuse in the all-sky camera.
Okay.
Oh, I see it.
Yep.
Yeah, okay. So we'll have somebody point it out on the screen there up in that about middle left. There is a little itty bitty meteor above Betelgeuse.
And
so cool. You're
in the right direction. It's pointing in the right direction for this evening to potentially be a Leonid.
Cool.
Yeah.
Awesome.
Very cool.
Sorry for interrupting you, Dennis. You can.
No, that's it.
Back to
yeah. So most of the, say, predictable annual meteor showers tend to be a bit older. So, for example, the Draconids I was talking about in my talk, they're very young. They're only several hundreds of years old. So you basically can either get hit by this very concentrated stream that's going to produce an outburst, or you're going to get nothing, right? Well, older streams, like the Perseids, every year they constantly produce about the same rate.
So I think that was a false alarm on the meteor, actually. You can see now in the next frame of the all-sky camera that streak has continued on. We should have said, I don't know if we said, these are 60-second exposures. So every 60 seconds, we're getting a new exposure. A meteor is only going to show up on one of those and not going to keep on going through the next 60-second exposure typically. And so the fact that we saw a little trail and now another trail, and I suspect the next image will have a trail, that's telling us that it's not a meteor at all, but likely a satellite. So false alarm on the meteor.
Oh, well. So our next question then comes from Dr. K. Carr. Dark sky is ideal to watch or photograph meteor shower. Does any horizontal or vertical component of artificial light destroy the clarity or sharpness of them? So I would just go ahead and say that any light pollution whatsoever is going to make your experience worse. Whether that's polarized horizontally or vertically or circularly, it doesn't matter. Extra light is going to be not your friend when you're looking for meteor showers.
It's really a contrast thing, right? So you're looking for faint objects. And so if you have a bright background, whether that's bright from a full moon or bright from a street light, you're not going to have the ability to distinguish faint things due to the high contrast against a bright background source. So contrast is what makes it hard to see faint things in bright conditions. But again, this new moon, the moon is not up tonight, and so it's a perfect night to be able to let your eyes adjust and hopefully see some meteors.
Fantastic, thanks. So it looks like we also just got another question from Desert Rat. Do you get non-meteor images from space junk?
Space junk, we don't see space junk that often because it's usually very slow. And when it re-enters, I guess when the bigger pieces re-enter, that usually happens over Pacific, but the smaller pieces we usually don't see. That's more of a problem if you're operating a spacecraft in low Earth orbit, then you're concerned about collisions, but not necessarily that we see something like that. The thing is, the stuff that's in orbit is moving at much slower velocities than normal meteoroids. And let's see, the conversion factor between mass and thus energy to light drops off rapidly at slow velocities. So we can't even see, let's say, centimeter-sized objects at 10 kilometers a second, which is kind of slow for meteor speeds. We can barely pick them up on meteor cameras.
Awesome, thank you. All right, so it looks like we're wrapping up here. I'll just invite anybody to ask any last-minute questions. And while you do that, I just want to remind everyone that this meteor shower can be seen from any location on Earth, and the best time to watch is going to be after midnight, before dawn. That's the beauty of meteor showers, is they're not as time-specific as people might think they are. So it doesn't look like we're getting any more questions in. So I'm going to go ahead and wrap it up and say thank you to Dr. Nick Moskovitz for being here, and thank you to Dr. Denis Vida, who's sort of like a guest star for us. And also thanks for everybody behind the scenes working, Danielle and Heather. And yeah, I think that's about it. Do you guys have anything else you'd like to say?
I don't think so. Thanks to everyone out there for watching. Thanks, Denis, for joining us in this virtual talk. Yeah. Yep.
Oh, and I see one last question. How many meteors per hour? About 10 to 20. Is that correct? Yes, 10 to 20 tonight. It is peaking. So get out there and watch. And with that, we're going to log off. So thanks, everyone. Have a good night.